Welcome to today's Explainer. We are about to go on a really fascinating journey to demystify the invisible forces that literally hold our entire universe together. Have you ever stopped to wonder why a tiny grain of salt stays intact? Or why a copper wire conducts electricity? Or why water, behaves so uniquely? It actually all comes down to the hidden microscopic architecture of chemical bonding. So today, we're going to make the invisible visible. Let's get into it. Okay, let's dive into this. Here is our cognitive roadmap for today's explainer. We'll start with 1, the quest for stability. Then 2, the metallic electron sea. 3, forces between molecules. 4, valence bond theory. And finally, 5, molecular orbital theory. Starting off with section 1, the quest for stability. Basically, why atoms form chemical bonds in the first place. So at the most fundamental level, individual atoms that have fewer than 8 electrons in their outermost shell are just inherently unstable. They are restless, they're highly reactive, and they are basically desperately looking for a solution. The ultimate prize in this quest for stability is defined by something called the octet rule. Atoms will absolutely hustle. They're going to gain, lose, or share electrons until they achieve an outer valence shell containing exactly 8 electrons. Now you might be wondering, why 8? Well, because that happens to be the configuration of the noble gases. You can think of noble gases as the Zen masters of the periodic table. They're incredibly stable and totally unreactive. And honestly, every other atom is just trying to reach that exact same level of inner peace. And this brilliantly illustrates exactly what we're talking about. Take a look at the sodium atom on the left. It's got one lonely, highly unstable valence electron. And then look at the chlorine atom beside it, missing just one single electron to complete its set. So in the ionic bond over on the right, they just trade resources. Sodium transfers its electron over, completely losing it, to become a positive cation, and chlorine happily takes it, becoming a negative anion. Now both of them have hit that magic number of 8 electrons in their outermost shell. They've essentially found stability through mutual electrostatic attraction. It's a perfect match. Moving right along to section 2, the metallic electron sea. This is all about sharing resources on a massive scale. Now, when you have a massive block of the exact same material, the rules kind of change. Metallic bonding isn't about localized pairs of atoms trading or sharing specific electrons, like we just saw with sodium and chlorine. Instead, I want you to picture this orderly, three-dimensional array of positively charged metal cations, and they are completely submerged in a shared, highly delocalized sea of valence electrons. Those electrons aren't tied down. They're relatively free to move anywhere they want throughout the entire piece of metal. Actually, think of it like a really crowded swimming pool. The people standing in the pool are the positively charged metal ions, mostly just staying in their general formation. The water itself, that represents the valence electrons. The water doesn't belong to any one single person, right? It pools together into this shared environment that just freely flows around everyone, and that shared medium holds the entire group together through mutual attraction. So here's a really interesting question for us to consider. If the valence electrons in a metal are like freely flowing water in a pool, how does that sea of freely moving electrons translate into the real-world traits of the metals we rely on every single day? Well, it explains perfectly why metals behave the way they do. Because those conduction electrons are completely mobile, they can easily transfer electric currents and thermal vibrations right through the structure. That is exactly why metals are such excellent conductors of heat and electricity. Furthermore, because the ions aren't locked into a rigid, localized bond like they would be in a covalent structure, the whole array is malleable. You can bend a sheet of iron or pull a chunk of copper into a thin wire, and that delocalized electron sea just shifts and flows right along with it without snapping or breaking. It's pretty amazing. All right, section 3, forces between molecules, the weak attractions that matter. Let's step back for a second and see how this builds. So far, we've only looked at the really strong bonds holding atoms together inside a substance. Now, let's zoom out and look at the forces acting between whole, separate molecules. These are called intermolecular forces, specifically van der Waals forces. And while they are definitely weaker, they are absolutely crucial for how matter behaves. The most universal, yet by far the weakest of these, is the London dispersion force. And it happens in a quick, chronological 3-step dance. First, you have a neutral atom with perfectly symmetrically distributed electrons. But step 2, remember, electrons are always moving, so for just a split second, more electrons might randomly end up on one side, creating a temporary dipole, a momentary negative and positive end. Step 3, This fleeting charge forces the adjacent totally neutral molecules to shift their electrons too, creating an induced chain reaction of tiny temporary attractions. You can actually see the visual mechanics of it right here. Notice how the temporary partial negative charge on the left literally pushes the electrons of its neighbor away, while its partial positive end pulls on them. It's distorting the electron cloud of the atom right next door. That is a London dispersion force in action. It is incredibly weak and it's super fleeting, but because it is happening constantly across all the particles in a substance, it's enough to hold nonpolar substances together. But what happens if a molecule is permanently lopsided in its charge? Well, that brings us to dipole-dipole forces. Unlike those temporary London forces we just looked at, dipole-dipole forces act between polar molecules that possess a permanent dipole. These permanent partial charges basically act like tiny little electric fields. The partially positive end of one molecule acts as a magnet, strongly attracting the partially negative end of a neighboring molecule. It's much stronger than a dispersion force, though keep in mind the attraction does decrease pretty rapidly as the molecules get further apart. And that naturally brings us to the top tier, the absolute strongest of the attractive forces between polar covalent molecules, the hydrogen bond. Now, despite the name, this isn't an actual chemical bond, but rather an exceptionally strong dipole-dipole attraction. But there is a very strict rule here. It only occurs when a hydrogen atom is directly bonded to highly electronegative nitrogen, oxygen, or fluorine. No exceptions. Now, what's really interesting about this is how it plays out with water. See those dotted lines? That is the hydrogen bond. The partially positive hydrogen atom in one water molecule is intensely attracted to the partially negative oxygen atom in a completely different water molecule. This specific, tightly knit network of intermolecular forces is exactly what gives water its high boiling point, and honestly, it's what makes life on Earth possible. Okay, Section 4, Valence Bond Theory, or VBT, upgrading our basic models. So as amazing as Lewis structures and drawing dots and lines are, they don't actually explain how bonds form in real 3D space, or why molecules take on very specific shapes. For that, chemistry literally needed an upgrade. The core mechanism of valence bond theory is beautifully simple but profoundly different from just drawing dots on a page. It states that a covalent bond forms through physical overlap in space. When the atomic orbitals of two atoms literally merge into the same region, they share a pair of electrons. The buildup of negative electron charge between the two positive nuclei provides the electrostatic glue that firmly locks the atoms together. Check out the formation of a hydrogen molecule right here. You've got two spherical 1s atomic orbitals. As they approach each other, they physically overlap. Now, maximum bond strength is achieved at a very specific, optimal internuclear distance. If they're too far apart, well, there's no overlap. But if they're pushed too closely together, those two positive nuclei will violently repel each other. VBT maps out this perfect, delicate balancing act of overlapping spheres. But science is this relentless process of refinement. And VBT, well, it hit a roadblock. It is fantastic for visualizing individual atoms overlapping their shapes to bond, but it couldn't explain certain magnetic properties or the complex energy levels of certain molecules. To truly understand molecular energy as a whole, complete system, the scientific model had to evolve yet again. Which brings us to Section 5, Molecular Orbital Theory, the final quantum leap. So the crucial point here is understanding a massive shift in perspective regarding chemical bonds. Instead of just picturing physical spheres bumping into each other and overlapping, molecular orbital theory, or MOT, actually uses mathematical addition and subtraction to understand exactly what happens to the energy of these electrons. In valence bond theory, individual atomic orbitals retain their basic identity. They just share an overlapping space. But in molecular orbital theory, those atomic orbitals completely combine and transform to form entirely new molecular orbitals that belong to the whole molecule, not just the individual original atoms. When these atomic waves mathematically combine, they yield two incredibly different results. When they add together, they form a bonding orbital. The electron density concentrates beautifully between the nuclei, lowering the overall energy and creating a highly stable attraction. But when the waves mathematically subtract, they form an anti-bonding orbital. Here, the electron density is pulled away, leaving a literal node of zero density between the nuclei. This drastically increases the overall energy level, causing the nuclei to actually repel each other, which threatens to tear the whole molecule apart. It's a constant tug of war. It is really incredible to think about, isn't it? We started this explainer looking at simple dots representing electrons just trying to reach the number 8. Then we moved up to physical 3D spheres overlapping, and finally to a complex mathematical model where entire waves of probability are adding and subtracting to create the physical reality of the objects you are touching right now. It really begs the question, as our scientific models continue this constantly evolving quest for accuracy, what invisible forces might we discover next? Thank you so much for exploring the invisible architecture of our world with me today. Keep learning and always keep questioning.